Hello. So for today's lesson, let's take a moment, pause the video and write down what I wrote already here on the board to save some time. So we're going to talk about pairs of lines, or in particular, we're going to talk about how to determine the relative position of two lines in the plane when you sketch the two lines. So as a motivation, equation of lines often represent constraints on business problems. And we will deal with this type of questions later on in more depth when we learn various algorithms on how to actually solve what we're going to call linear programming problems. So this is basically like one of the most basic types of problems that can be solved with, with linear equations. So the position of these lines in the plane gives clues on their solution. So basically by looking at how these two lines, which again often represent constraints on business problems, looking at the position of these two lines, we can figure out, or we can gain some information about the existence of solutions of that problem. So let's actually write down an example. Suppose we have a firm, a company that produces two types of items, A and B, let's say. And let's say that item A costs $2 per unit to produce, and item B let me write it down again. So, and item B costs $3 per unit. And let's formulate a question that leads to our topic of today. Can this firm produce, so can it produce 10 items and can they do that using let's say $26? I'm choosing some small numbers with purpose of having some nice or easy numbers to compute to begin with. Okay, so if you put into math these questions, notice that both questions essentially are constraints on the business problem, right? So I want to produce, or the firm wants to produce 10 items, and they want to do this by spending precisely $26. This is a little bit restrictive because you will see later constraints often are formulated also in terms of inequalities. For example, if I have $26, the question is, what's the optimal production using at most $26? So that not exactly 26, but maybe less than 26. But let's say I want to spend precisely $26 and I want to produce 10 items. So when we put this into math, obviously we need some variables. So let's denote by X the number of units or items. So the number of items of type A, and by Y the number of items of type B. And if we look carefully, the two constraints form two equations of two lines. So let's see how that comes to be. If I want to produce 10 items over here, that means the sum of the two variables x plus y should be 10. If I want to use precisely $26, then the total cost of production, since type A costs $2 per unit, I have to multiply that by the number of items produced, so 2x, add to the cost of producing y units, $3 each, so 3y, and this should be $26. So I want both of these to happen at the same time. So both of these conditions need to happen at the same time, which means we form basically a system. of two linear equations. And what I want to emphasize is that it's not obvious right away whether actually we have a solution, how many solutions do we have in case if we have any. And that's actually related to the position of the lines, if you were to sketch these two lines. Let's actually try to solve the system using elimination. This is one of the mainstream of the methods we're going to use in this class. Most of you should know how to solve a 2x2 system via elimination. What we're going to learn today is a more sophisticated method based on the elimination, in fact, to deal with much larger systems than just with two unknowns. So elimination typically means that you need to multiply one or both equations by some convenient coefficients so that we can cancel one of the unknown and then solve for the other. So for example, if I want to eliminate x, I can multiply by -2 the first equation, the entire equation. And after I do that, when I add the two, -2x plus 2x is 0, 3y minus 2y is y, 26 minus 20 is equal to 6. So I have y equals 6 as a solution, and then I can use a quick substitution. For example, I can go back to the first equation and substitute y with 6 and solve for the other unknown. So as it turns out, the answer is yes. You can produce exactly 4 units of type A and exactly 6 units of type B, given these two constraints. Now, if you were to sketch the two lines, the geometric interpretation is that the two lines will intersect at precisely one point. Because think about it, remember in the previous lecture, an equation of a line means the conditions on the points, on the coordinates of the points on the line. So basically, the two lines should have a point in common if we were to have a solution of this system. So let's actually sketch the two lines. You can plug in any 2 points for each line, and that gives you, then you can sketch the equation. So for example, let's plug in 0 for y. So obviously x plus y equals 10 goes to the point 10, 0, and 0, 10. Let's say this is 10, and that's one of the lines. The other one, I don't think it has nice numbers. For the other line, let's see, if I plug in 0 for y, then x will be 13. And if I plug in 0 for x, y equals 26 over 3, which is 8 point something, right? So that means the other line, so when x is 0, y is 8 point something, so it's further below 10. Let's say this is 26 over 3. And if y is 0, x is 13, which is further to the right of 10. So that's the other point of the other line. And let's sketch it. And then the intersection point that we just determined, the solution of the system will be 4 and 6. So the two lines are intersecting, which means there is precisely one solution. Now, let's modify a little bit the problem. Let's say the firm wants to use precisely $50 to do the same thing. Now, the two equations in that case, if I still want to produce 10 units, is x plus y equals 10. And actually, let's make a slightly... so let's make an additional condition. Let's say the price is $2 per unit for both. A little bit unrealistic, but let's just say that the cost of production is really the same and the two items differ than, just color, let's say, right? So, otherwise the price is the same of production. So if the price is 2 units for both of them, then the second equation will be 2x plus 2y equals 50. Okay, now notice something on the second equation, and that's another good habit to have later. If we can make the coefficients smaller by simplifying all the coefficients from left and right, we should do that often. unless we have a reason not to. So here we can divide the second equation by 2, and that means the second equation, x plus y equals 25. It's equivalent to the first one. It should be obvious that without even trying to solve the system, that there are no solutions for this system. I mean, the two pair of lines or the two equations cannot happen at the same time. Each of them independently, of course, has plenty of solutions. You can find infinitely many points on each line, but obviously x plus y cannot be simultaneously equal to 10 and 25 for any pair of points. Now, geometrically, that means the two lines are parallel, so that means they will never have a point in common. So when you sketch the two, basically they have the same slope, but they are distinct. They're not the same line. So one of them goes to the point, again, 0, 10, 10, 0. And the other one, I'm going to basically squeeze it here because it should be much further to the right, goes to the points 25, 0 and 0, 25. So the two lines are parallel, which signifies that the two constraints cannot happen at the same time. On the other hand, let's say I want to make a slightly extra modification. Let's say I want to produce, let's say I want to actually use $20. So same data as above, but $20. That means I produce 10 units, cost of production is the same for both, $2, so 2x plus 2y should be $20. Again, just like before, if I divide by 2, notice that in fact the two constraints are really the same. It was in a slightly different form, the second constraint in the beginning, but by a simple algebra modification, or in this case a simplification by 2, a division by 2, we notice that the two equations are really the same, which means that the two constraints lead to the same mathematical constraint. They might be different from a business perspective. I mean, the first one means the number of items produced. The second one means the allocated monies that you spend. But mathematically, it just happens that they are the same. So in this case, of course, the two lines are coincident. They're really the same. And that means you have infinitely many solutions, because there are infinitely many points that satisfy both equations, which is really just one of them, right? So I mean, when you sketch it, basically you have just, let's see if we can squeeze it here, you have basically just one line that, you know, superimposed over the other. So two lines superimposed that go through the point 10, 0 and 0, 10. So now obviously examples of possible solutions are, let's say you want to figure out some solutions are 1, 9, 2, 8, and so on and so forth. I'm saying infinitely many solutions because let's say you can produce fractions of an item, right? So for example, another possible solution is 1.3 and 8.7, right? So the sum of the two is 10. Obviously, if you have to produce just whole objects, because I should have mentioned before, another condition is that if you really, you know, want to make it realistic, another condition is that these are positive if x and y really represent real actual objects. So in fact, when you look at the solution space, you don't look at the negative region of the plane. But we'll deal with that later when we talk about more realistic constraints depending on the problem. So for one, let's focus on the interpretation that the relative position of two lines essentially gives you a clue on existence of solutions in problems like this. And they don't have to be business problems, but again, that was just my motivating example. So on the second page, let's actually write down these three situations, intersecting, parallel, and coincident, in terms of a formula, if you want. Because the way to actually figure out, or let's actually see how we figure out in general the position of two lines, kind of like a small algorithm, if you want. So let's see if this actually works, because last time was a delay when I moved to the second page. And let's see. Okay, so let's continue. As I said already, there was a break actually when I turned the page. I should figure out at some point how to do this faster. So the goal again is to determine the relative position of two lines. So let's actually formulate some sort of an algorithm on how to do this. So how to determine the relative position of two lines. There are various ways to do that, but I would say that the standard way is to write both lines in a slope-intercept form. So that means both lines, let's call L1, L2, the two lines, should be written as y equals something. So just get y by itself on the left side, and that gives you the slope-intercept form. M1x plus B1, let's say, is the first line, and the second line M2x plus B2. So basically you have three possibilities. If the slopes are the same, remember the coefficient of x in the slope-intercept form is the slope of the line. So if the slope are the same and the intercept is the same, obviously the lines are coincident. They're the same essentially. If the slopes are different, then the lines are intersecting. And if the slopes are the same, but the intercepts are distinct, then the lines are parallel. So that's, you can determine the two relative positions without actually doing, without sketching it, right? So let's go over a couple of more examples. So suppose one equation is 2x plus y equals 4, the first line, and the second one is 2x minus y equals 8. So if we get both of them in the form of slope-intercept, so I can leave y on the left, move 2x on the right, 4 minus 2x, or minus 2x plus 4, and move y on the right, 8 on the left, and start with y. So that means y equals 2x minus 8. Okay, so notice that the slopes are minus 2 and 2, which are distinct. So we are in the second case, and the lines are intersecting. Which means, in that case, we can compute the intersection point. So for example, if the question is to find the intersection point, you solve the system by elimination. By the way, some of you are used to solve the system by substitution. From now on, try to abandon that method, because with 3 or more variables it's very impractical, and that's one of the reasons the major part of the course is to learn some sophisticated algorithms of dealing with larger linear systems, which are essentially fancy elimination methods. Substitution is far too tedious if we have 3 or more variables, and in general it's faster even in 2 variables. Notice here we just all I have to do is to add the 2 to eliminate y, and that gives me x equals 3. And then I can you can use the substitution to find the other one. That's going to be easier. So I can plug in, for example, 3 in the first equation, 2 times 3 plus y equals 4. That gives me y equals 4 minus 6, which is minus 2. So the intersection point of the two lines is always, remember, starting with the x coordinate is 3 and minus 2. So that's the intersection point. Let's do another example. Let's do example 1. So the second one, let's say the first line is 4x minus 2y equals minus 7. And the second line is minus 2x plus y equals minus 2. So let's do the work again to leave y by itself. Move 4x over, keep y on the left, move 2x or minus 2x over. Here we have to divide by minus 2. Don't forget to change the sign. So minus 4 over minus 2, that gives me 2x plus 7 over 2. And the second line is 2x minus 2. Now notice the slopes are the same. 2 equals 2. But the intercepts, the y-intercepts to be more precise, are distinct. 7 over 2 is not minus 2, not equal to minus 2, which means the lines are parallel. So indeed, if we are to sketch them, so let's start with the first line. We're going to have to deal with some fractions here. So if x equals 0, y is 7 over 2. That's like 3 point something. So let's say 7 over 2 is here. And if, so for the first line, if y, if y equals 0, x is minus 7 over 4. Which means minus 7 over 4 is on the negative side somewhere here. It's like minus 1 point something. Remember, you just have to basically place the point in a reasonable position relative to the others. And because now you know that the two lines are parallel, you can basically write them parallel. You don't have to actually count the units there. So the other line, let's see if x is 0, y is minus 2. So let's say minus 2 is somewhere here. And then you can just draw the parallel line because you know already the two lines are parallel based on the fact that they have the same slope. So what does it mean if these are constraints of a business model, or if this is a system? In other words, this will be inconsistent. This is another name for no solutions. So when you have two or more equations or inequalities, as you will see later, if it's not possible to have at least one solution, we call that system inconsistent, which is another way of saying there are no solutions. So that's it for today. Don't forget, as soon as possible, preferably immediately after this lecture, after you go over the lecture and after you make sure you understood all the steps in the example, try to do the homework right away, because it will save you a lot of time, because the material is fresh in your mind, so you could do at least a couple of problems and maybe finish it later. But don't do the homework too later, because then you're going to forget some of the stuff and you'll waste more time that way. Okay, I'll see you next time.